We know the power, we know the mass, and we know the final velocity. We want to find out the amount of time it takes to get to 100 miles an hour. We can look at energy. The sum of the change of energy of this thing is 0. Well, we could also say the sum of the change of energy is equal to the work that you put in it, which is equal to force times delta x, which is equal to the power times the change in time. So what we can see is, yeah, we put power in for a period of time, and that gives us some energy. How do we see that energy? Oh, well, if we're driving up a hill, that would turn into potential energy of mgh. But that's not the case. This is on the flat, and all of the energy that we put into it is turning into kinetic energy. I like that. How about the change in momentum is 0? Again, you could say, who is the car exchanging momentum with? The car is gaining momentum in this direction, and the Earth is gaining momentum in this direction. Okay, the Earth is big. We don't have measurements on it. This isn't going to be helpful. Force is equal to mass times acceleration. The acceleration we don't know. We don't know the force on the car, so this probably won't be very helpful. And the motion, the kinematic equations. We don't know the acceleration. We don't know the velocity. We don't even know the final displacement. And we don't know the time. So these formulas are not going to be helpful to us at all. Let's go to the one we know. Let's first convert our units. So the power is equal to 100 horsepower, but there are 750 watts about in a horsepower. So that's equal to 7.5 times 10 to the 1, 2, 3, 4 times 10 to the 4th watts. Okay? Or 75 kilowatts. How about the speed? V, final, is equal to 100 miles an hour. And I know that a meter per second is about 2.2 miles an hour. Right? So we need to divide that out. And it's about 45 meters per second, I think. Because if I multiply 45 by 2, I get 90. If I multiply 45 by 2, I get 90. 2.2, I get 99. That's close enough to 100 for me. So I can say, look, I can find the kinetic energy of this guy when I finish, because I know the mass, and I know the power I put in, and I just want delta T. So I'm all set. Delta T is equal to 1/2 mv final squared divided by the power. So 1/2 times 10 to the 3rd kilograms times 45 meters per second squared divided by the power, which is 7.5 times 10 to the 4th watts, which is a joule per second. Let's take a look at our units. We have a kilogram meter squared per second squared. That's a joule. So this is all a joule, and the joules cancel, leaving me with seconds in the denominator of the denominator, and I like it because that winds up being seconds in the numerator. Now the number. Okay, so let's take a look at our exponents. This is 10 to the 3rd, and that cancels 3 of those 4. The 1/2, we can bring this down, and that gives me a 15 here. And then I got two 45s. So I can write this as 45 times 45. This cancels one of them, yielding a 3. And so I have an answer. There's a 10 in the bottom, right? And I've got 45 and 45 times 3, 45, 45 is 90, that's 135. Divided by 10, that's equal to 13.5 seconds. About. So now we know the time is about 13.5 seconds. And we want to know the force at that 13.5 seconds. The force when the velocity is 100 miles an hour or 45 meters per second at a power of 7.5 times 10 to the 4th watts. So again, we do the analysis. How about energy? Change in energy equals 0. What I can say is, let's take 1 second when I'm going about 45 meters per second. And then I can say, oh yeah, the energy is the work I put in, which is equal to force times delta x, which is equal to the power times delta t. and I know delta t, I'm saying it's just 1 second. I'm just taking that 1 second where I'm going really fast, and I'm multiplying it by the power, so I'm going to get 7.5 times 10 to the 4th watts times 1 second. A watt second. Oh, what's a watt? A watt is a joule per second, so the seconds cancel. So I have 75 kilojoules of energy that is put in by the engine during that time. And I can find the total displacement because the speed is about 45 meters per second. I'm getting going a little faster because I'm accelerating, but it's about 45 meters. And so I can find the force during that second. And so the force is equal to 7.5 times 10 to the 4th joules divided by 45 meters. Let's check the units. A joule is a kilogram meter squared per second squared. This cancels one of the meters, and so I like it because I have a kilogram meter per second squared as a newton. And then I've got 75 kilojoules divided by 45, so it's going to be on the order of 2,000 newtons, a little bit less than that. And actually I used a calculating device and got 1,700 newtons, about 1,700 newtons. Okay, is that a big force? Well, if you remember that F equals ma, we can find the acceleration, force divided by mass, and with 1,000 kilograms that we're accelerating, that's 700 kilogram meters per second squared divided by 1,000 kilograms. I'm getting an acceleration of 1.7 meters per second squared. Is that a lot of acceleration? Not so much, not near as much as gravity. But you would feel that that's like, in 1 second, I'll increase by 1.6 meters per second. So 1, 2, something like that. It also means that it's not a bad estimate to say the speed is 45 meters per second during the whole second, because it only goes up to 46.7 by the end of the second. So it's a reasonable estimate. And then you say, but Pete, we didn't do the other analysis. How about I can just use kinematics, because I know that acceleration is change in velocity over change in time, right? And that's just 45 meters per second divided by 13.5 seconds. Yielding, I don't know, what, 3.5 meters per second squared. And then I take the force, is mass times acceleration, and I end up with, you know, on the order of 3,500 newtons. Why isn't this right? Okay? And the reason is that this is the average acceleration, the total change in velocity over the total change in time. And is the acceleration constant under this scenario? It's not. Okay, we know that when you first accelerate in a car, a powerful car, you're going to get a lot of acceleration until it's going very fast, then your acceleration drops off. So because the acceleration was very high in the beginning, your average acceleration, 3.5 meters per second squared, is higher than the acceleration at the end, which is, what did I say, 1.7 meters per second squared. Let me explain it in a different way. This is an important formula. That power is equal to the change in energy over change in time, or the work over change in time. Right? But work is force times displacement in a certain period of time. Well, guess what? That's velocity. So force times velocity is the power you put in. So if we were to graph this, the force on the car as a function of the velocity, it would be a hyperbola. Meaning, when you first start out, if your engine is dissipating 100 horsepower, the force on you is infinite, and it drops off with higher speed. Now, of course, you can't get that infinite force, and it's good you didn't, because it would kill you, right? Because the force is too much for the tires, and it spins out. And then as you get faster and faster, you find that the force, and hence your acceleration, is going to drop off. Okay, so how about our energy conversion? What we want is we want kinetic energy. We want the car to be moving very fast. Where did that come from? Well, we put gas in it. That's chemical potential. So that's potential energy in a chemical form. Okay, so we put the gasoline in, and it turns to kinetic energy. Wait, directly? It just, Like our muscles take ATP and do work. No. The gasoline goes in and it explodes and expands. That's a heat engine. So it turns to heat energy. This is very important. Okay, so the chemical potential energy turns to heat energy. Right now, keep in mind, this isn't 100% efficient because the engine itself dissipates a huge amount of heat. So you lose a huge amount of heat here. Okay, now where did that chemical potential energy come from? Well, that came from prehistoric plants that got compressed over many years. So this is plant matter, potential energy chemical of plants. Right, and we know where that came from. That came from sunlight, radiant. That's our sun looking out for us. Okay, so where did the kinetic energy go? Well, ultimately, we're moving molecules around, or we hit the brakes and they get hot. This all turns to heat. Okay, even if it makes sound, that ultimately turns to heat. And where does that go? That goes to the infrared radiation out into space. And keep in mind, this was very inefficient. Most of the sun's energy also turns to heat, and all of this is radiated out into space.